So we are still in the revision of what we have covered so far, and we reached to the issue of the atmospheric attenuation of the solar radiation. Then talking about, we have seen a figure like that in chapter 1, talking about like uh, energy bands showing the fraction of the solar energy falling up or within a certain wavelength and indicating what is the midpoint of the wavelength. And this is given for a certain condition, a certain place. And definitely tables like this should be available for several places throughout the world. This is processed data, it's not raw data. And the processing here has been done by one of the softwares available, which is called SmartS or Smarts, which is basically takes the raw data and does a certain processing for the data so that you have clustering of the energy band and the corresponding wavelengths, among other sort of treatment of the raw data so that it comes in an organized way. What we have here is another interesting way of estimation of the average solar radiation, which is basically showing the solar radiation above a certain threshold and the number of hours in a day where substantial solar radiation are falling. A certain value would be selected as a datum. For example, assuming that we are going to estimate how many hours the solar radiation in a day exceeds a value of, say, 150 watts per meter square, because this is where you can get an effective amount of energy that you can use it for running any application. And this has been done here in front of you for several locations in the world. And what we are getting here basically, or these numbers, the number of hours that we have here, is what we refer to in a symbol as N bar, and the symbol is being given here. Why I'm stressing this? Because we are going to use that in our calculations a little bit later. This was data that I just found that's related to several cities within the kingdom, and it shows average daily total radiation and the normal radiation, so this is basically divided in different places within the kingdom. So it shows that we have substantial amount of weather stations that are there. Maybe I mentioned last time that the weather stations doesn't have to be sophisticated and large things on an institution level, but anyone can run an experiment. He can have his own small size devices that would measure the solar radiation, temperatures, humidity, wind speed, and so on.
Doctor,
Yes.
can you remind me what was WH mean? You said something about hour, but what is per second? So I'm still confusing.
Your question again.
The WH. I think you said what per hour, but what is per second? So I still confusing.
Yeah, what basically is joule per second, but sometimes because we are not going to integrate the values of solar radiation over a second, normally you need to expand it on a certain period of time where you can use it. That's why we are using the hours a lot. So instead of talking about joules as a total amount of energy, it is expressed in terms of watt hour. So it's a way to express the amount of energy integrated over an hour, which is taken as sort of the smallest time span for expressing the solar radiation. And then you are averaging the values over the hour.
So it's the joules per hour, right?
It's not really joules per hour. You can say that it's integrated amount of energy for over an hour. Yes.
Okay, thanks.
What we are looking at here, this is probably is where we almost stopped last time. We're looking at this equation where we are using an empirical equation, which is referred to as the angstrom type regression equation. And we can use this for measuring the monthly average daily radiation ratio to a clear radiation, so monthly average over clear radiation, and it's given here in terms of a couple of empirical constants, and then small n here represents the number of hours on a day where the sunshine is above a certain threshold, where n here, capital N, is the monthly average of maximum possible daily hours of bright sun. And we have ways to calculate each one of these. The constants are basically given. The small n bar can be taken from a figure or a table like the previous table that we have seen, whereas the capital N, we have taken an equation in chapter 1 to calculate it. HC here is the monthly average clear sky daily, which is not easy to determine, and this is why they came up with a modification to this equation where the HC is, or the clear sky solar radiation, is being replaced by the extraterrestrial radiation, which can be calculated either through a formula, an equation that we have taken in chapter 1, a figure, or a table. So we have enough ways to calculate the extraterrestrial radiation, and we are going to replace the HC by HO, as you can see it here in equation 272. So in order to calculate the value of H, then what you can do, you can use the extraterrestrial radiation, which can be found for any place, depending on the location and the time. A, B are constants. The value of n bar can be found in a table, and capital N can be found either on a table or a graph or an equation. So these are values that are available, out of which you can calculate this ratio. And this ratio is always referred to as average clearness index. We are going to use that a lot when we come to the applications of solar collectors starting from chapter 6. In this slide, it's telling where you can find the information of HO. HO can be found in equation 110.3, or can be found in tables or a figure as well, where the value of capital N can be found in one equation. I'll be showing this equation in a while. And you can also show it or see it in a figure where you can extract it from the figure. The constants A and B are normally given so that you can make use of this information to calculate the value of H. Now let's consider an example. The example is based on, again, the information related to Wisconsin-Madison, and definitely you can have this in any place in the world. For example, here, the values of the constants A and B, the range, and the sunshine hours in general, in percentage of the possible, is being given here. And this is given in several places in the world, including Wisconsin-Madison, where we are going to make use of our equation there. So the values there for Wisconsin are 0.3 and 0.34 for both the empirical constants A and B. Here's the example. It is asking to estimate the monthly average total solar radiation on a horizontal surface in Wisconsin-Madison, which has a latitude of 43 degrees, based on the average duration of sunshine hour that's available in the data, in the table. The table 271 is basically this table that we can use to calculate the value of small n. So here we are going to get, for Wisconsin-Madison, we're going to come up with a value here, which is representing the month that has been specified in the example. So back to the example again, it is asking for monthly average total solar radiation on a horizontal surface for Wisconsin-Madison for this latitude 43, based on average duration of sunshine hour as given in the data. The estimates are based on the equations and tables that we have covered previously. Looking at the tables, you'll find that we have values of A as 0.3, B is equal to 0.34 from the previous table, table 272. The values of H are obtained from a figure 110.1. You can also get it from a table 110.1, this is all in chapter 1, or there is a formula which is given us the value of H naught as a function of phi and delta. And the day length, which is capital N, can be taken from equation 1,611, or you can take it from a figure in chapter 6, which we have shown, in chapter 1, which we have shown earlier, that can be used for calculating the sunset hour as well as the capital N, which is the duration of the sunshine during the day. So the desired and values that are being calculated are tabulated in a table. If you notice that in this example, that the value of the month, or the month is not specifically given, which means that it is needed to be calculated for the whole year, for every month. These are the data that we are going to use basically. So the value of each node can be obtained either from an equation, or from a figure like this, or from a table like that. Then you can get the value of each node. The easiest one of them is to deal with the figure, but as I mentioned before, as engineers used to like figures because they can give quick values right away, but we have a problem with the accuracy in the calculations, because when you are getting the values from the figure, you are getting some sort of approximate numbers. You can do interpolation in tables like this. If you need to be very precise, you might need to go to the equation. The value of capital N can be either obtained from an equation like this, or there is a figure also that can be used to get the value of N based on phi, the latitude angle, and delta, which is the inclination angle of the location. And then we are going to substitute those in this equation. A and B are constants. They are given in the table for the city, Wisconsin-Madison. And then the small n is obtained from the previous table, capital N from this equation. Each node is from this figure or that table, and then we can get the value of H. So this has been done here, and the process has been made for these months, as you can see it here. And when we are coming about these months, when we are talking about the months here, then we are following what we have here in this figure. And in each month, we are getting the data on the representative average day of the month, which is given here. So for June, it will be June 11. For July, it will be July 17. Each one of these is a representation of the average value of H over the month. And the values of each node are obtained from the figure, and they are all listed here, or from the table, it depends. And then the capital N is obtained by using this equation here, 2 over 15 cosine minus 1 tan phi tan delta. And you know how to calculate delta. It's been given there in our first chapter, in chapter 1, which is the inclination. N over N, so we have N obtained from the table, capital N is obtained from here, and then the estimated value of H from the equation, from this equation, is being calculated in this value here. Then what are the other, or couple of columns? Actually, our calculations end here at this point. Identifying the month, getting the value of H naught from the figure or the table, calculating capital N, obtaining N, small n, from the table, and dividing capital N over small n over capital N, substituting into the equation to get the value of estimated H. Actually, what we have here is some sort of a verification to the data that have been calculated. This figure here is measured values, which means that there's some sort of instrumentations alhamdulillah, have been used to estimate it. So remember that we are using this data normally if we don't have measured data. So this has been given here as a special case for verification. And there's another thing that was recommended, which is if you are in an area or in a city, and that city does not have enough data, does not have radiation data, then you may need to get radiation data from a nearby city so that they are almost close to each other in terms of calculated values. And that's why Blue Hill is a region which is very close to Wisconsin-Madison, and the values that are estimated over there are known. Accordingly, some sort of a comparison between these values and these values will tell us that yes, I mean, you can do that. You do not definitely expect 100% accuracy of the data. If you say that I don't have the information of Wisconsin-Madison and I'm going to go for Blue Hill information and use it, you would use it, but you have to be cautious that it might not be exactly fitting the values that you have. There is some sort of differences between the values here and there. Accuracy of the empirical information that we have taken is measured against the, or actually is tested against the measured data. It's not very accurate, it is roughly, but it's acceptable because normally as engineers, we know when you are doing your calculations, you are keeping a margin of a factor of safety. So if you are calculating or you are estimating how much solar collectors are needed for a certain location to cover what we call a solar fraction of 0.5, then if it is 0.51 or if it's 0.48, that's something, it's a tolerance which is acceptable normally in this application. I mentioned an expression which is called the solar fraction, and the solar fraction is one of the terminologies which is used in solar energy applications. If, for example, you need to have a certain instrument that you need to run or a certain load of heating that you need to have, and you have your original source, which could be electricity or fuel, and you are going to say that I'm going to replace the load, 50% of the load by solar energy, then we'll say that the solar fraction is 0.5. So it determines how much of the load that you have, be it load of heating or load of electricity, how much of it you need to realize through the sun. If you want to go 100% renewable energy, then you say that you are going for a solar fraction of 100%. Otherwise, it's always some sort of a fraction. This is the comment I just mentioned about a comparison of the figures that we have or the table that the calculations were done. We've done the calculations ourselves through the correlation, and we had measured values, and then we had data of a nearby region, and we had a comparison between the three of them. Then another thing to consider, maybe it's the last to consider in this part of the presentation, talking about the estimation of clear sky radiation. This is related to the effect of scattering of the radiation in the atmosphere and absorbing. We said that there is attenuation or reduction of the solar radiation due to both scattering and absorbing. Scattering by solar or dust or sand particles or maybe water vapor droplets that are suspended in the air, whereas the attenuation is being done by either the ozone layer, carbon dioxide, or water vapor that can absorb part of the radiation before it falls to the ground. So it is useful then to have a standard clear sky expression and calculate the hourly and daily radiation that can be received on horizontal surface under these conditions. A method of estimation of the beam radiation transmitted through clear atmospheres has been proposed by Hotel, that it takes into consideration the location. So the Dennis angle and latitude are considered in this equation, and the atmospheric transmittance have been calculated here. Remember, when we're talking about the properties or radiation properties, last time we were talking about three properties that you have covered in heat transfer earlier. One of them is the absorption, the other is transmission or transmittance, and the third one is the reflectivity. So here we're talking about the ability of the atmosphere to transmit the radiation and how it can be calculated. And the values are being given here. It's a function, again, we have three constants, A1, A2, and K, and we have cosine theta z, which is basically cosine of the zenith angle. So it depends on the location. And this has been done assuming a clear visibility of 23 kilometers. However, some of these constants can be available for different values or different reference of visibility or clear visibility. The clear sky normal radiation would be then defined as a ratio of GON, which is the terrestrial radiation falling or normal terrestrial radiation falling outside of the atmosphere. And this can be calculated here for different days based on this equation. This equation, I just copied it from chapter 1. Instead of saying that, you may refer to equation number 141, A or B. So I just brought it here so that you would know how the value of GON can be estimated. It's the solar constant, and then the constants and cosine 360N is the number of the day throughout the year, starting from 1 at 1st of January and ending with 365 at 31st of December. And then talking about the clear sky horizontal beam, so that's why the zenith angle is being considered here, cosine the zenith angle. And this applies for the irradiation, instantaneous radiation falling onto the surface, and it can also be given or be applied on the integrated value of the solar radiation over an hour or a day or a month. So the same idea would be there. So that's all to estimate the clear sky radiation, or the clear sky index as we call it. And some estimation of this value has been given here, where the diffuse coefficient can be calculated and be related to the beam coefficient of the solar radiation, which is falling into a surface. A simpler method, as usual, is to use a figure based on the zenith angle. You can get the value of the G, or the G beam radiation, or the normal radiation falling into a surface. So refer always, or that has been always the case, the trend when people started with this, it was the 80s, and the 80s and the 70s were the period where there is tendency of utilization of figures for quick calculations or estimation of values, knowing that the accuracy is going to be affected, but it's not going to be affected we can say in an adverse manner, or will not be too much affected, but it's something that can give what we say easy back of the envelope calculations. That was all before the existence of computers. Now people would just refer to softwares to do this kind of calculations right away. Clearness index, KT, is again defined as H over H naught. H naught again is the extraterrestrial radiation. The information that we are given here can be given as H over H, or it can be given as I over I naught. The same thing can be done, or the same kind of concept or meaning can be applied here. So it can be given as instantaneous H over H naught, or it can be over integrated period of time. So the value of I over I naught can be given here. And the integration can be over an hour or over a month, as you can see. So that was a continuation to what we discussed yesterday. And then we're going to still go through a completion or a second part of the presentation, which is associated with this chapter. So I'm sharing with you here the remainder or a continuation of that, in which now what we're looking at is the beam and diffuse components of hourly radiation. And note that we're going to be repeating the process that we're going to start now, looking first at the hourly radiation data, and then looking at the daily radiation data, and then the monthly radiation data. And you'll find that we are having some sort of a similarity between the three. The only difference is what is the time span that we are considering. So we are going to review the methods for estimation of the fractions of total radiation, which are basically diffuse radiation and beam radiation. Looking at or considering that there are variations in the ways of the calculations that have been done, but luckily, this kind of variations are not resulting in so much differences in the end results. So end results are basically, which means that you can apply different ways, but at the end you are going to come up with almost very much close results. So let's continue with this and know that there's this substantial agreement between the data which are produced in different either different correlations or using different correlations versus figures or tables. The split of the solar radiation on a horizontal surface is basically done to diffuse and beam components. Um, it is interest to us for different kind of applications. The method of calculating the total radiation for different orientations on a horizontal surface needs some sort of separate treatment of beam and diffuse radiation. As we will see a little bit later when we come to the applications, there are some devices that basically depend on the beam radiation primarily. Some other devices are basically considering the diffuse radiation. So being able to calculate these fractions and know what is the beam radiation, what is the diffuse radiation for each location, for every time is an important issue. In terms of instrumentation, we have seen when we started this chapter that there are instruments that can measure beam radiation alone, diffuse radiation alone, and then total radiation. So having a lot of this data or raw data available, processing the data is one of the things that are proved to be very much useful in the applications. The estimates of long time performance of most concentrating collectors is based on the availability of beam radiation. So that's again one of the applications where beam radiation plays an important role. So we're still looking at beam and diffuse components of hourly radiation, and there's a useful approach to calculate the ratio between I diffuse over the total I, this fraction of the hourly radiation on a horizontal plate, the diffuse components, where the value of KT is I over IO, hourly clearance index. So we have the value of KT, and we need to calculate the diffuse component of the radiation. Now, a lot of data have been considered and collected, and the data have been processed all as you can see here in this figure by Reindl. That was in 1988, where is given a relation between ID over I versus KT. This is a correlation, and he collected the data for many locations, and it can be in figures similar to these figures, and it can be divided into ranges where the value of KT can be estimated. A set of points would be the basis for a correlation. Within each group or cluster of the data, there is distribution of points. For example, a KT of 0.5 can be obtained in different conditions. It could be a condition of sky with a thin cloud cover, so we are talking about a high diffusion fraction, or a sky which is clear for a part of the hour and heavy clouded on the part of the hour that leads to a low diffusion fraction. Which what it means to say here that the way you are interpreting the data is very important. Talking about a value of k t is equal to 0.5 is interpreted in different ways or can be realized by different ways. And we should be aware of that while we are dealing with the data, which means that the correlation may not be representing a particular hour very, very closely, but for a large number of hours, it would adequately represent diffuse fraction. Then we have similar data that have been processed by Orgel and Holland for Canada, in herbs and others in the US and Australian stations as well. And then Rindel have used independent data coming from the United States and Europe. And actually, they came up with three correlations to give us the relation between that fraction and KT. And the correlations I've seen here. Interestingly, the three correlations are given values that are not too far from each other, which means that we can use some sort of an approximate correlation to represent the figure that we have here. We can say that we have three clusters of the value of KT, and the values have been collected from a large number of stations in US, Canada, Europe, and Australia. And yet, you're getting some sort of values that are close to each other. Actually, they are essentially, looks like that they are almost identical, although they are coming with three sets of raw data or three databases of raw data. Then Herbst came and he made a correlation, and the correlation has been given here. Three values of the ratio I diffusion over the total incident radiation energy. And this has been given for a range of KT from 0 up to 0.22, which is the upper first part of the curve, and then the sloped part of the curve, which K ranges between 0.22 to 0.8, and then finally for K is equal or greater than 0.8. So now this whole data can be clustered, or actually it can be confined in a correlation, and the correlation here is being given as a function of the range of KT, and the function of KT is given here, either a linear relation at the first part of the figure, or a polynomial in the second part of the figure, or finally almost a constant value for the third part where KT is greater than 0.8, which is something again that can be represented lightly by one line as you can see it here. Now, this data is, is it something that is agreed upon? Actually, not really. You can hardly find something which is processed in terms of raw data that's agreed upon. But some people would say that, no, there can be other readings where the value of KT in the last cluster greater than 0.8 is not really constant, but it's increasing a little bit. So it would not be surprising to find somebody come in and say, no, I'm going to create another correlation which is going to be represented. And the point is he has to prove the point. He has to come up and say that if I'm going to compare it with experimental data, then this is what we get. And this is how close it would be to the data that have been measured. Same thing has been done for the ratio of Hg over H as again a function of KT. To remind you, KT is basically the daily total radiation divided by the daily extraterrestrial radiation H over H naught. And in the last part of our previous presentation, we were showing that there is a correlation that will give us H over H bar as a function of H over H naught. And that was a function of A, B, N, and capital N. Here we are not too far from that. We are talking about correlations that or figures that can be correlated or put in an equation form that can represent the daily total diffuse radiation over the daily total radiation Hg over H, and this is given as a function of KT, which is a representation of the daily total radiation H divided by daily extraterrestrial radiation H naught. To remind you again, H naught can be calculated, or actually it's obtained either through a correlation, which is in chapter 1, or through a figure or a table. So the value of H naught is easy to get. Now, these data that we have here are representing different places all over the world. Each one of these scientists or researchers has focused into a certain area where he got his figure from, and then they have been clustered as you can see it here. Some of the data by Stanhill which is the dotted lines, have done the data in Palestine actually. I'm talking about the MENA region, but it was in Palestine. And then Chaudhry, which is this line with short vertical lines here, is by Chaudhry, and that has been calculated in New Delhi. The Canadian station, which is actually been considered by Chan, Truller, and then for Hyatt in Australia and Bannister, and then the rest are basically US calculations. So some values are being clustered all together and gathered so that we can see that qualitatively speaking, we have the same trend or the same kind of relation between the ratio between HD and H and KT or dependence on KT. Then processing the data again, Herbs came, and remember, Herbs was the one who made the correlation previously, and it seems that this is basically what he was trying to do, looking at this kind of data and try to come up with a correlation, an equation that can represent the figure or can be a best fit to the data given in the figure. And he has made a classification to the readings that is based on the sunshine angle. You can see here the value of, or the sunset angle, which is WS. And you can see it here for WS greater than 81.4, that the upper figure, whereas the lower figure would apply for WS less than 81.4. And we have an equation for calculating the sunset angle that we have covered in chapter 1 as well. What he came up with, you can see it here in this figure, the ratio between HD and H can be given as the upper equation for WS, the sunset angle less than 81.4, and the values are given here for different values of KT, and for spring and summer and fall, in which WS is greater than 81.4, then the values of the ratio HD over H can be given by this equation. So he came up with these kind of equations and clustered it based on the seasons, spring, summer, and fall in one hand, and winter on the other hand, and it has been specified by having the sunset angle and the onset was 81.4. Again, the equation that we see here have not been derived mathematically. These equations have been processed in statistically from a large number of raw data that are available. We have an example here to look at. This example is talking about the day's total radiation on a horizontal surface for St. Louis, Missouri in the United States that has a latitude of 38.6 on September 3. The value is being 23 megajoule per meter square. Estimate the fraction of diffuse energy and the amount of diffuse energy as well. So what we're going to do here, we have a certain location identified by its latitude angle, 38.6. The day of the year has been given, September 3. And the total radiation has been given as 23. What we need is the diffuse radiation, HD, and the ratio HD over H. H here is the 23, which is given here. Accordingly, we can come up with the value of delta, and delta, I just brought the equations where we need these values and I put them here as a reminder for us. So delta is being calculated from this equation. It's a function of the day of the year, and here the year or the day of the year is September 3. So there is a table, I think it's table 161 in chapter 1, where you go back and see what will be September 3 in terms of the year. So what does it represent? Or if you wish, you can do it on your hand. For example, January is 31, February is 28, March is 31, April is 30, May is 31, June is 30, July is 31, August is 31. You add them all together and then you add 3 because it's the 3rd of September. And then you can put the value of n, calculate delta, in which you can find delta equal to 7. Then calculate the value of WS, the sunset angle, which is given as tan phi tan delta. Phi is being given as 38.6. delta have been calculated as 7, and WS is equal to, accordingly, 95.6. So we're going to go for the correlation corresponding to WS is greater than 81.4. And we're going to use the equation that we have for the value of H naught. And again, H naught, as I mentioned earlier, you can get it from a correlation like this, which is equation 110.3, or you can get it from a figure or get it from a table. You have the table and the figure 110.1 that can provide us with the value of H naught. Then, when you do that, you'll find that H naught is 33.3. Now, value of KT is basically H over H naught. This is H, and H naught have been calculated, so the ratio that he's looking for is the 0.69. And the value of H is 23, so the diffusion fraction of this is the 0.26 multiplied by the H, which is 23, and then you can get how much of the energy falling is diffuse energy. So we had an example here that is enabling us to see out of the total radiation falling into a certain horizontal surface over a certain period of time, you can estimate how much of it is diffuse radiation and how much is beam radiation or direct radiation. Remember that because we are going to get to that later when we come to the applications. So what we are doing, again, I need to emphasize that currently what we are doing is that we are laying the foundation. We are just preparing the tools that we can use after that for analyzing applications which are relating to solar energy. I would probably here just hold for a while and go through the attendance. Abdul Hadi, Abu Zaid. Abdul Hadi. Abdullah Abu Shaya. عبد الرحمن المشحف.
Yes, Doctor.
يوسف المحيش.
حاضر يا دكتور.
عمار الثوملي.
Yes.
حسين الوحيد.
نعم.
صالح البليهي.
Yes, Doctor.
عبد الله الدوسري.
Yes.
عمر الجهني.
Yes.
عبد العزيز المقثوي. عمر الشمري.
Yes, Doctor.
عبد العزيز الشهري.
Yes, Doctor.
ريان الودعي.
Yes, Doctor.
فهد الزهراني.
Yes, Doctor.
عبد الرحيم بيمة.
Yes, Doctor.
نواف الكعبي. نواف كعبي.
Yes, Doctor. Yes.
أحمد خواج.
Yes.
أحمد سندي. And Yasser.
Yes, Doctor.
Okay. So I'm getting a message from Abdullah Bushaya that he's here. So, okay, fine. Actually, just to make sure that you are
Doctor?
with me. Yes, go ahead.
Did you hear me?
Who's talking?
Saleh Blahi.
Saleh al-Blahi. Did I record something against your name, Saleh, here? No, I guess I considered you present. I think I did.
Okay, thank you.
Okay. What I'm going to do later is that I would probably put some sort of a poll every now and then to make sure that you are with me. So just randomly at any time in the lecture, I would just probably put a question and ask you to put what you think about this question or so that we can just to make sure that you are with me in as as we are processing in our next, and I mean, starting from the next class, inshallah. And just to remind you again that I just put a note, an announcement today in the Blackboard that a week from today on next Wednesday, we are going to have a quiz. The quiz is related to chapter 1. You are going to submit the homework of chapter 1 on Sunday, and accordingly, once I receive the homework, after that, I'm going to post the solution of the homework in the Blackboard, and we're going to have a quiz which is very much related to this homework on Wednesday, inshallah. Now, I've been looking into the hourly data. Now we're going to shift gear into the monthly data. As you can see it here, we're going to talk about charts which are similar to the ones that we have used earlier, and a process which is very much similar to the one, but here what we are looking for basically is monthly data or monthly fraction of the diffuse radiation divided by the total quantity which is falling. And again, it's the same thing, HD over H as a function of KT, where KT is nothing but H over H naught. And H naught, to remind you, it's the extraterrestrial radiation. And this can be found basically either from equations, tables, or charts. So these data are basically collected from daily data, and either by summation of the daily data or some sort of processing through a generalized daily curve of HD over H versus KT. So the figure, the raw data can be processed and be given here, and see what you have seen in front of you here. It's basically sort of monthly data, and it has the monthly average daily diffuse radiation, HD, divided by the monthly average daily total radiation versus the value of KT, which is H over H naught. And again, this has been given by several researchers, and the values are being recorded here. Again, the values have been clustered by herbs in 2 lines. One of them is a representation of a case where we're talking about summer, spring, and autumn, where the value of the sunset angle is greater than 81.4, and winter, where the sunset angle is less than 81.4. And then these values have been put in a correlation, and the correlation has been shown here. So it's a polynomial, basically, which is providing us with values of HD over H for this range of WS, or the sunset angle. And keeping in mind that this correlation is more accurate between KT is equal to 0.3 and 0.8. Why is that? Because the figure basically is limited to this, note at the figure. So the figure, the data that are given are limited to this value. Accordingly, he had to put that limit so that no one can be saying that safely I can extend it for values of KT less than this range or beyond that range. If you do that, you know that you are going to do some sort of what we call extrapolation, and then the accuracy is not guaranteed because there's no way to compare it unless you have data for the comparison. So the values of HD over H are given here for different or for 2 ranges of the sunset angle. And what we are looking for here is the monthly data. Then let's have an example on that. Estimate the fraction of the average June radiation on a horizontal surface that is diffuse in Madison, Wisconsin. Again, we're talking about Wisconsin, Madison, so values that we need here might be taken from the previous example, where basically from equation 110.3 of calculating H naught, again, H naught can be calculated either from a correlation or from a figure or from a table, and then for the latitude and the declination of 23.1 delta, because we're talking about June, so you selected the day of June, which is June 11, according to what we see in the figure, if you remember. And for June 11, you can get the value of H naught from the figure as 41.8. KT is 23. We have calculated 23. It's actually taken from the previous example, or it's taken from the appendix where the information are given for the average daily radiation. So H bar in Wisconsin Madison is 23. We calculated H naught, or we obtained it from the table as 41.8. So the fraction basically is 23 divided by 41.8, which is 0.55. From the equation, WS, or the sunset angle, is 113.4, and then we can use that equation that we have just seen a while ago for WS greater than 81.4, which is this equation with the value of KT that we have, and then you can calculate HD over H. And accordingly, HD over H has been calculated to be 0.38. Now, what we're looking here is, what if we need to estimate the hourly data from the daily data? So it might be necessary to start with the daily data and again, rely on what people have done that have considered statistics or statistical methods to extract the data. So the studies of time distribution of total radiation on a horizontal surface through a day using the monthly average data of the number of stations led to generalized charts. So charts are the A for the ratio between I and H, which is the ratio between hourly data to the daily data as a function of the day length and the hour that you are interested in. And there's a figure that shows this chart. This figure has been basically developed by Leo and Jordan, by Willier and Hotel and Willier. So these are the base of generating a figure like this. The hours are designated by time for the midpoint of the hour, and then the days are assumed to be symmetrical over the solar noon, which means that solar noon would be there, and then before the solar noon 1 hour, and after the solar noon 1 hour, they will be identical. So there's some sort of a symmetry over 12 o'clock or 12 noon. And the figure is being given here. So that if you have the solar hour, which is the top figure, and then half an hour before or half an hour after, 1.5 hours before or after, 2.5 hours before and after, and so on. So if we are talking about, for example, at 9:30 in the morning, it's going to be 9:30, 2.5 hours away from the solar noon. So that would be a representation of the value of I over H for this case. So the day length N can be calculated from an equation that we have taken in chapter 1. I've just shown this equation today, the calculation of the capital N. Or you can take it from the Wheeler diagram, which is 163. So knowing the day length, which is a function of the latitude and the declination, knowing the daily total radiation, the hourly radiation can be obtained from here. And I said it's symmetry. So what you get at 9:30 in the morning would be the same as what you get in 2:30 in the afternoon. The figure is based on long-term averages, has been considered for data which are representing a large number of days, and it's intended for determination of the averages of hourly radiation. The curves that we have in the figure can be also represented by an equation, and the equation has been given here. So what you see here in this figure can be also represented mathematically in equation, which means that we have a couple of ways here. If you are doing your hand calculations, maybe the figure is going to be the best thing to do because it's easy. All you need to do is how much is the hours from the sunshine to sunset, which is something you can get easily, which is the capital N. And knowing what hour of the day that you want, and then you can get the ratio right away, just from the figure right here. Or if you are putting that in the context of some detailed calculation that you are putting in a program, you cannot put a figure in a program. So what you need basically is an equation. And here the equation would solve this problem. So RT is being given as a function of the hour angle, omega, the sunset angle, and a couple of constants. They are not really constants, A and B, but they are given as a function of the sunset angle. Quantities or coefficient as a function of the sunset angle. Substitute these values, calculate A and B, substitute A and B here, and then you can get the ratio RT. And you know that we have taken equations that will enable us to calculate the hour angle. If remember, it is 15 into the current hour minus 12, which is the solar noon, and then the value can be calculated. There is a correlation for WS, the sunset angle, that we have seen today also, and then you can calculate the value of RT accordingly. A direct example again has been given here. Talk about what is the fraction of the average January daily radiation received on Melbourne, Australia, between 8 and 9 o'clock. So for Melbourne, you just find that phi, or the latitude angle, is 38, and then the mean day of January is 17th of January. You get that from table 161. From equation 161 for calculating the declination angle, you can get it as equal to minus 20.9. And the daily length, capital N, is 14.3. The daily length here can be obtained either from the correlation or an equation that gives capital N, or through the Fourier diagram that based on the latitude and delta, you can come up with this. Actually, through that figure, you can get the value of N, which is the length of the day, and you can get the sunset angle as well, sunset hour, I'm sorry, as well. Then substituting into the equation, which is, into the figure, which is this, knowing that what is the hours, the N, capital N, which is the total hours of sunshine during the day, hours from sunrise to sunset. You can put the value of N here. And what time that you are looking for. Here it is asking us to calculate between 8 and 9. So between 8 and 9, the hour is going to be 8:30, which is somewhere in the middle. 8:30, which means that the deviation from the noon is going to be how many hours? From 8:30 to 12 o'clock. This is going to be, hey, anybody with me?
Three and a half.
Yes, 3.5, exactly. So what you do here is that you are going to get from the capital N value 3.5, and then you can get the ratio from here. So this is basically what has been done in this example. So for 3.5 hours from the solar noon at a day length of 14.3 hours, approximately the ratio is 7.8. So 7.8% of the radiation is going to be in that hour. Or you can use the equation, and which is the correlation that we have seen in the previous figure here. We are talking about an hour angle. So you are going to substitute for an hour angle of 8:30 in the morning. You get to the correlation or the equation of the hour angle. You can get the value of WS that can be obtained from an equation. And then you are going to substitute that and get the value of RT. When you do that, you are going to get a value of 0.076. So that was 0.078. This is 0.076. So it's an acceptable accuracy to go through the table or the figure. Maybe you can see now that going through the figure is going to save a lot of time instead of doing lots of calculations. But this is definitely on the expense of accuracy, which means that the 0.076 is expected to be more accurate than the value of 0.078. And probably again, I just iterate that I mentioned that before. If you are going to solve this example, all of you, then some of you are going to get it as 0.8, some will get it as 0.7, some will get it as 0.9. It's just the issue of the estimation of the eye when you are looking at a certain point in the figure, or in the y-axis, which is representing the ratio. Another example, the total radiation for Madison on August 23 was 31.4. Estimate the radiation received between 1 and 2 p.m. So it's the same thing. We're just looking between 1 and 2 p.m., which means that the deviation from the solar angle is 1.5. Then we're talking about Madison. So Madison, the latitude angle is 43. You substitute and get the value of delta on August 23, and you need to see what's N for August 23. Again, add up the months together until you reach for August 23. And for the value of N, you substitute in the equation of delta so that you can get delta. Here it's equal to 11. So delta is 11 and phi is 43. And then the sunset would occur at 6.45, where the day length, capital N, is 13.4. And again, to get these values, either you'll get substitute into the equation of the sunset hour, omega s, and the value of capital N, or go to the Willier chart, which is in chapter 1, based on the latitude and the value of delta, then you can get these two values right away. Then we are going to substitute into the figure again with a day length of 13.4 and a mean hour of 1.5. We're talking about 1:30 p.m. And then the ratio is going to be obtained as 0.118. This is RT. So the RT here represents the ratio between I over H. And in that example here, the value of H has been given. Accordingly, you can get the value of I for that hour here, which is 3.47 megajoule per meter square, which means that this 0.118 is basically I divided by H, and H is 31.4. Then multiply the 0.118 into the 31.4, you'll get 3.7 megajoule per meter square, which is the amount of radiation that has been emitted over this hour, which is basically between 1 and 2 p.m. We have a figure here that shows a set of curves for RD. Here we are talking about the diffusion or the diffuse fraction. So similar to what we have seen earlier. Earlier it was for the total radiation. Here we are talking about the diffuse radiation. And some sort of a similar figure has been shown here. And here the ratio basically of ID over HD is given RD. So the subscript D is used here to indicate diffuse radiation. So what you see here in front of you is very much the same as we have done previously, but the focus here is on a component of the incident radiation, which is the diffuse component. So a figure similar to the previous one, exactly. I mean, qualitatively, it's the same way that you need to calculate what is the sunset hour angle, or what is the value of capital N, get to the capital N, what time of the day, so that you can see how far you are from the solar noon, how many hours from the solar noon, and then you can get the ratio between the hourly diffuse radiation divided by the daily diffuse radiation. Daily diffuse radiation would be given so that you can get the hourly diffuse radiation at any hour. So the value of RD can be obtained from this figure, or it can be obtained from this correlation, which is again some sort of a curve fit to what we have here in this figure. And an example again is given to estimate this, which is basically the same thing that we have seen earlier. But as I just mentioned, that what we are looking for here basically is the diffuse component of the radiation, not the total radiation which is falling. I think I will stop here for that presentation, and then we'll continue with the rest of this chapter from our next class, inshallah. But the point here is what we are able to calculate now. We are able to calculate the monthly solar radiation, the hourly solar radiation for any location throughout the world. What you need to do is the latitude angle, what's the inclination angle, and based on this value, you can calculate the sunset angle, the duration of sunrise during the day. Once you have these values, that you can obtain that daily radiation on a horizontal surface, or even the hourly value. So these are values that you can obtain, which means that maybe I would just recommend a lot that hopefully you don't pile the material. You can see here that we are dealing with so many equations and so many figures. Some of them are repetitive, but you should be aware to distinguish between them. So why don't you just, while you're studying this, say that I want to do this for my own city. Suppose that you are from Jeddah. Try to do that. For example, in Jeddah at 1:30 in the afternoon as of today, Wednesday, what's the amount of solar energy which is falling? So that's something that you can calculate. So try to do that as an exercise. And I think that you can build interest on that, because eventually, maybe you can get a special assignment of this course asking you to come up with a design for water heating requirements for your home at so that it takes care of like 60% of the total hot water needs. And that's something you're going to need this type of information for. So I'm going to stop now. It's 9:45, and then we'll continue next time, inshallah. Reminder, on Sunday, you are going to submit the homework, and on Wednesday, we are going to have a quiz, inshallah. So we'll see you next time, ya shabab, inshallah.
يعطيك العافية دكتور.
الله يعافيك، شكرا جزيلا.